Let's drive the DeLorean into the radians today and go to Back to the Future National Day with Marty McFly. All right, here we go. This lesson is about radians, and so far we've talked about degrees. It's a shift in thinking. It's a big day because radians are used more frequently than degrees when you get into higher math. So we want to understand what radians mean. We're going to set up this unit circle the same way as before, where we knew that these were 0, 90, 180, and 270 degrees, as well as 360. I'm going to come back to this, and I'm going to write in the radian measures instead of the degree measures so we can start thinking that way instead of degrees all the time. The section is 3.2 on radians and degrees, how to convert between the two. What does a radian mean? And so the first thing we have to remember are basically some ideas with circumference, which is 2 pi r, and if I divided both sides by 2r, I'm going to get pi is equal to the circumference divided by 2r. There's not a reason right now why I would divide, by 2r, other than to identify what pi is, but radians are mostly labeled in terms of pi. And so we want to think about something like circumference divided by an r to get my answers in terms of pi. And you'll see what that means in just a little bit. In this part, you're going to see that the main definition is right here. And the main definition for theta in radians is s divided by r. And s refers to arc length. And your r refers to a radius. So theta in radians, which is just like in degrees, but instead of degrees, it's radians. It's just a different way of labeling an angle, is equal to the arc length divided by the radius. Now, what does that look like in terms of a circle? It looks like an arc length s divided by the radius r is going to give you your theta in terms of radians. So this theta now, when you take your s divided by r, you're looking at your theta in radians, giving you an actual measure. That's why this is important where you're dealing with the circumference divided by 2r. It's like the whole circumference, but we're going to get into that. We're looking at arc length divided by r. Well, the question here is, what would 1 radian equal? 1 radian would equal where your s is equal to your r. So, for example, over here, your theta is 1 radian. Why? Because this length here and this length here are equal. When I divide my arc length by my radius, I end up with 1, which means my theta is actually equal to 1 radian. S divided by r is equal to the radian of theta. 6 divided by 3 is equal to 2 radians. That theta is 2 radians. You're going to have a button on your calculator. You don't have to change now, but you're going to be comfortable switching back and forth between radians and degrees when you have to in any type of problem. But know that if a story problem gives it in terms of radians, you're going to have to switch your mode so it's calculated in radian mode. In the book, you're going to see that the book doesn't always label if it's radians. In fact, a lot of times it'll leave radians out. And so when you see a degree, you know it's in terms of degrees. When you see 2 without any degree, it means 2 radians. They won't put radians in the book. They'll just leave it as 2. You'll have to know that it's radians you're dealing with. So without any degree, you know you're talking about radians. The book gets sloppy that way. How do you convert between degrees and radians and vice versa? You know that one full rotation all the way around the circle is in radians is going to be 2 pi r, which is your circumference all the way around your arc length, divided by your radius, which is r. And look what happens. Your r's cancel and you're left with 2 pi. 2 pi is the radian measure all the way around the circle. I'm going to go back to this slide and we're going to go ahead and mark down what we're talking about with radians versus the degrees shown. This is going to be 0 radians. This is going to be 2 pi radians, because we just found that out. 2 pi r divided by r. And then I can figure out the quarters as I go around the circle. So half of 2 pi is now pi. Half of pi is pi over 2. And then this one is going to be pi plus 1/2, which is going to be 3 pi over 2. These are my new guiding angles when I go around the unit circle. I want to make a point now also that you're going to have to add fractions and change 2 pi and pi to fractions that you can easily add and subtract other fractions with. So, for example, pi can also be labeled as 3 pi over 3, 4 pi over 4, or 6 pi over 6. And we'll get to why we want to do that in a little bit. But sometimes we don't want pi, we want to use these fractions so I can easily subtract or add like denominator fractions. Similarly, 2 pi, we're looking at 6 pi over 3, 8 pi over 4, and 12 pi over 6. If I know one full rotation is 2 pi, I know 360 degrees is 2 pi as well. And now I can get a relationship between the two. I divide by 2, and I get 180 degrees is equal to pi radians. There's my conversion. 180 degrees and pi radians. That's how I'm going to go from one to the other. This isn't going to be the conversion. It's just telling you, roughly speaking, 1 degree is equal to pi over 180 radians. If you took pi divided by 180, that's how many radians are in 1 degree. And all I did here was divide by 180 on both sides. On this one, pi, I know that if I divide both sides by pi, then I'm going to get 1 radian is equal to 180 divided by pi. 1 radian is equal to 57.3 degrees. That will tell you how wide 1 radian basically is opening up. I want to just do a quick example to show that there are 2 methods in solving and converting 45 degrees. I have definitely a preference. I'll do that first, but then there's another way if you prefer it. Just pick one way and go with the way that makes sense. 45 degrees to radians. How do you convert? I would start with 45 degrees, and then I want to multiply by the conversion factor. The conversion factor is going to be 1 pi over 180 degrees. Now notice the order that I'm doing. I want to find radians, so I'm actually putting the pi up on top. I want to get rid of the degrees, And if you think about those labels, they will cancel because you have one on the top and one on the bottom. So at this point, you want to just cancel, and so this is going to end up as pi over 4. 45 goes into 184 times. So 45 degrees is actually equal to pi over 4. Converting back, pi over, oh, I'm sorry, let me go back and show you the other method. If that confuses you, you can also do a proportion. So I can say, all right, I want to know the radians, so I'm just going to say radians over my 45 degrees is equal to pi radians over 180 degrees. And if you were to multiply both sides by 45, you're going to end up with the same thing that we did up here. 45 times pi divided by 180. And you're going to see that ends up being pi over 4. This is my top method is much easier. That's what I'm going to continue with. But if that makes more sense, you can do that. Going the other direction. Converting from radians to degrees. I want the degrees on top of my multiplier, my converter, and then I'll end up with the degrees. So this becomes pi over 6 times, I want the degrees on the top, 180 over radians on the bottom. The radians would cancel, and you're going to see that this is going to be left with 30 degrees. Your pi's would cancel. 6 goes into 180 30 times. So 30 degrees is actually pi over 6. These are special angles, and you're going to be dealing with these over and over and over as you go through. So I'm going to, again, go back to that unit circle, and I'm going to draw in these common angles that I'm finding. This 30 degrees now is actually pi over 6. This 45 degrees, I just found out before, was pi over 4. And the 60 degrees is going to be pi over 3. These are now going to be your new reference angles. Just like 30, 45, 60 were reference angles, those are now your reference angles. So we now have, we're thinking in terms of fractions, radians, and we're getting out of the degree mode. Convert 4 pi over 3 to degrees. Same idea as before. 4 pi over 3, 2 degrees. You want degrees? I'm going to put the degrees on the top, 180 degrees, with the radians on the bottom. And now we're going to be simplifying that multiplication. Again, since we're multiplying numbers, we can divide out, leaving ones. We can divide out. And so this is going to be 4 times 6, or 240 degrees. It's converting between the two. If you actually get it, you do not have to write this down. I would say if you're comfortable with what you're multiplying and in what order, then you wouldn't have to write this down. This is showing you how to go from degrees to radians and radians back to degrees. And you're seeing that these are just reciprocals of one another. It's not like you have to memorize which one you're multiplying. You should always be thinking, what am I trying to get? Put that on the top, and then the labels will cancel what you need. I'll come back to that slide if you need it later on. Don't write this down either. This is the unit circle I passed out a while ago, and a lot of you are using it as bookmarkers. And I just wanted to show you a couple of things on here. Notice that this now has radian measures in it. Pi over 6, pi over 4, pi over 3, pi over 2, pi, 3 pi over 2, 2 pi. So that's where those numbers are coming from. Also notice this. If this is pi over 6, notice that this is 5 pi over 6. Why is that 5 pi over 6? This is pi over 6 here, and you're taking pi, which is really 6 pi over 6, and subtracting off pi over 6 and getting 5 pi over 6. How are you getting 3 pi over 4? You're taking pi, subtracting off pi over 4, and getting 3 pi over 4. You're either adding or subtracting these reference angles to getting these other angles as you go along. These are subtracting the reference angles. This is adding the reference angles. This is going to be subtracting the reference angles from pi. Same idea, just with fractions. On your big rock sheet, you're going to have this table in chapter 2. And if I were you, I would want to use the same exact table, but only add one more row in, and that row would be the radian row. And that can either be added up above or down below. But the main thing is that you're getting comfortable with the new measures in that table. You could memorize that 3's and 6's go together. 30 degrees is pi over 6. 60 degrees is pi over 3. You could also remember 30 degrees, the bigger number has to go in the denominator to make it smaller, so that's why it's pi over 6. 60 degrees, the smaller number has to go to make it a bigger number. Smaller number has to go on the bottom to make it a bigger number, so that's why it's pi over 3. Don't always convert between the two. Start thinking about radians and dealing with fractions. If you always convert, you're going to be spending a lot of extra time in this class. You want to get comfortable with those fractions. The sooner you can do that, the easier this chapter is going to be. This is a section that just is going to show you that we can develop the same ideas. These triangles develop the table. You don't have to write the triangles in. I'm just showing you from the same triangles that we developed the table before, you can do the same thing with radians. Pi over 4, 45 degrees, you know the sign of pi over 4 is going to be opposite over hypotenuse, 1 over radical 2. This is still the angle, it's just in radian mode. If the question is what's the sine of pi over 3, I'm actually just looking up at the triangle. Pi over 3, that's my bigger angle, so it's going to be opposite over adjacent, radical 3 over 2. Going back to cosine of pi over 2. Cosine of pi over 2 I cannot do in those triangles, so if you remember, pi over 2, I have to go back to the unit circle because it's on one of those axes and pick a point, 0, 1, and then your r is going to equal 1, so you have your x, y, and your r. Cosine is x over r, which means it's going to be 0 over 1, which means it's just going to be equal to 0. That should look familiar, picking your x, y's, and r's and your points. Sine of pi over 4. Going here, 1 over radical 2. Not too bad. Or radical 2 over 2. Next one I want to skip. Go to cosine 3 pi over 2. Cosine 3 pi over 2, that's down here. Again, get a point. Cosine is x over r, which is 0 over 1 or 0. Now I want to spend a little bit more time on D and F because they require a little bit more effort. First thing is on D, we're going to do it the same way we did it with degrees. We're going to draw it, we're going to find the reference angle, and we're going to rewrite it in terms of reference angles. So the first thing I want to do is draw this. So I have to figure out where does 5 pi over 3 belong on the unit circle. Well, when I draw this, I'm thinking, all right, this is pi, and this is 2 pi. Is 5 pi over 3 closer to pi, or is it closer to 2 pi? The answer is 2 pi, because it only takes pi over 3 to get to 2 pi. I'm thinking 6 pi over 3 really here. 6 pi over 3, and this is only pi over 3 away from 6 pi over 3. So when I draw this, I can really draw that in, and I can also say my reference angle is pi over 3. 5 pi over 3 plus pi over 3 is 6 pi over 3, which is 2 pi. Got my reference angle. I also remember Santa Claus, everything else is the same. Tells me it's negative. I rewrite negative sine pi over 3. And then go to my table. Don't have to deal with the triangles. Go right to my table. Sine pi over 3. I'm thinking that's the bigger angle, so it's going to be negative radical 3 over 2. Sine of the smaller angle is 1/2. Same steps. I'm not doing any converting between the two. I'm just doing it in radian 1. Cosecant 5 pi over 4. 1 over sine 5 pi over 4. I'm thinking, okay, where is this particular angle? It's a little bit more than 4 pi over 4, so it goes in the third quadrant. Reference angle, pi over 4. Rewrite negative 1, because its tangent is positive, negative 1 over radical. This way it's easier to just say it's 1 over radical 2 is the sine of pi over 4. That makes simplifying easier if you can switch the form of that, because now it's just going to be a negative radical 2 form. Or you can say it's the reciprocal of the sine of pi over 4. Should actually put one more step in here. I should have had a negative 1 over sine of pi over 4. So it should be 1, 2, 3, and 4. Rewriting with this reference angle and then evaluate. These do require a little bit of steps. Don't take shortcuts. There are a lot of mistakes that can be made. The last thing that you could write down, you don't have to. The book makes a big deal out of this, and it's saying basically how you can get your reference angles. We've shown how to get them with degrees, but you can do the same exact system with radians. Notice that pi is just substituted for your 180s, and 2 pi is substituted for your 360s. By thinking about radians and not doing all this converting back and forth, going into the future, back to the past, back and forth, that can get very confusing. So stick in one and you'll make your life a lot easier.